Hi everybody, and welcome to the first video for Chapter 12. Chapter 12 is about fractals, and if you haven't seen a fractal before, it might be worth your time to just do a Google image search of the word fractal. Fractals are incredibly beautiful pictures, first and foremost, and the reason that we are studying them is because, because they're really pretty. I mean, there's there's no reason not to study them for that reason. They're just incredibly beautiful objects. But also they show up in nature all the time, and their construction demonstrates all sorts of interesting mathematics. So this won't be the most applicable chapter that we will do. The most applicable chapter was probably chapter 10 about financial things. But in my opinion, it's the most interesting chapter, just because fractals themselves are inherently interesting. And in this video here, we're going to do sections 1 and 2 of chapter 12. We're going to talk about two different fractals, the Koch snowflake and the Sierpinski gasket, and we'll talk about self-similarity as an attribute of fractals. So let's begin with the Koch snowflake, and I actually don't know how to pronounce that. I say Koch, but I don't really know. Could be Cook. But anyway, our first example of a geometric fractal is a shape called the Koch snowflake, and it's named after this dude who died in 1954. Like other fractals, the Koch snowflake is constructed by means of what is called a recursive process. It's a process in which the same procedure is applied repeatedly in an infinite loop. The output at one step becomes the input at the next step. So that probably doesn't mean too much to you, but you'll see what it means as we look at the construction of this figure. So to begin construction of the snowflake, you start with a shaded equilateral triangle, and we will refer to this starting triangle as the seed. So the seed is always sort of the start point of the construction. The size of the seed triangle is irrelevant, so you can just assume that the sides start with length 1. So it's equilateral triangle, all three sides have length 1. Okay, so the first step to building the snowflake is to the middle third of each of the sides of the seed, add an equal triangle with sides of length 1/3. The result is this 12-sided, star, snowflake, whatever. So the important thing to note here is that why did we choose 1/3? Well, when we glue an equilateral triangle right here with side length 1/3, that means that this side length here is 1/3, as is this side length down here. So over in this figure here, the original equilateral triangle is like this, and this side length here is 1/3, 1/3, 1/3, and 1/3. So every linear piece of this thing has the same length. Everything is side length 1/3. And so, of course, you can do this again, right? You can just take this figure here and on every straight edge, just glue an equilateral triangle to the middle of it. So we're going to put an equilateral triangle there, right there, right there, etc. And we will get a picture like this. Okay, now in this case, the side length of the equilateral triangles we glue on will be 1/9. So back in our original picture, we took side lengths of 1/3 and glued them on. Well, 1/3, of course, was 1/3 of 1. So the side length here was 1, so we took 1/3 of that, which gives you 1/3. Now the side lengths, like of this triangle here, the side length was 1/3. So now we have to take 1/3 of 1/3, but 1/3 of 1/3 is just 1/3 squared, which is 1/9. So in this picture here, every side length is 1/9. And of course, you can see how this goes. We just keep doing this. So for ease of reference, we will call the procedure of adding an equilateral triangle to the middle third of each side of the figure procedure KS for Koch snowflake. This will make the rest of the construction a lot easier to describe. Notice that this procedure makes each new side of the figure crinkle into 4 new sides, and that each new side has length 1/3 the previous side. So if we were to take this figure and do the same thing, so on every single straight edge, we glue a little triangle to it right in the middle, that new triangle, the side lengths will be 1/3 of 1/9 now, and 1/3 of 1/9 is 1/27. And that's exactly what we get right here. In the third step, we get a more elaborate snowflake with way more sides. Each has length a third of a third of a third, which is 1/27th. And you can keep doing this, right? Now, eventually, you won't be able to tell a difference from the naked eye, right? This already is pretty small here. So steps 5, 6, and 7, you keep doing this, but you have to be able to zoom in pretty far to see anything. So at every step of this recursive process, and by the way, that's just what recursive means. It just means you do the same thing over and over again. Essentially, that's what it means. So at every step of this process, you get a new snowflake. After a while, you can't really see anything with the naked eye. So soon enough, the images become visually stable. You keep doing the process, but your naked eye can't tell that you've done anymore. So for all practical purposes, we are seeing the ultimate destination of this process, the snowflake itself. So the snowflake itself is what you obtain by doing this process infinitely many times. So it's one thing to just say that, right? Just do this process infinitely many times. You may very well wonder, well, what does that mean? Doing something infinitely many times. And we don't really have the tools in this course to unpack what that means. So just pretend like that makes sense. You can make it make sense, but it takes more mathematics than we're capable of in this course. But in any case, the Koch snowflake is what you get. Replace 6 here with a billion, then a billion 1, billion 2, etc. You have to keep going. The end result, after infinitely many steps, is the snowflake. One advantage of recursive processes is that they allow for very simple and efficient definitions, even when the objects being defined are quite complicated. So this snowflake is pretty complicated, but we can define it in 2 lines. Oh yeah, so 2 lines of text. Using a form of shorthand we will call a replacement rule, a rule that specifies how to substitute one piece for another. And this is the only rule. So at every step, replace a straight edge with a crinkled straight edge, right? So you replace this edge with the same edge, but you've crinkled the middle of it, so that now there's an equilateral triangle thing sitting here. And notice that's all we did in these pictures. So here was a straight edge, right? Straight edge, straight edge, straight edge. All we did was we replaced each of those edges with a little crinkled edge, and that gave us, this figure. So this straight edge right here, what used to be a straight edge, has been replaced by a crinkled edge. And that's all you need to do, that's all you need to specify to get the snowflake. Just, hey, at each step, replace this straight edge with this crinkled edge. If we only consider the boundary of the snowflake and forget about the shaded interior, we get an infinitely jagged curve known as the Koch curve, or sometimes the snowflake curve. So just to be explicit here, in this picture, just imagine removing the interior shading. So what's left is this sort of jagged, boundary curve here. That's what it's talking about. So that's what's called the snowflake curve. So we'll just randomly pick a small part of this section and magnify it. So the surprise is that we see nothing new. The small detail looks just like the rough detail. Magnifying further won't help anything. So let me just show you. So imagine taking this part of the boundary curve and zooming in. You will see this, which looks identical to what you started with. And suppose you take this magnified piece and you zoom in some more. So just pick a piece to zoom in on. You see the same thing you started with. So you can do this as much as you want. You can magnify 1 billion times. You will see the same thing. So magnifying or zooming out has really no effect on what you see. The only caveat to that is that we've decided to magnify on these points that actually point to the right, So if you magnified right here, it might not look exactly the same as this, but the idea is the same. If you started by zooming in on this, and then zooming in on this, and then zooming in on this, you'll see the same thing. So the Koch curve, the way that you describe what we just said, where you can magnify or zoom out and you won't change the actual picture, that's the idea of self-similarity. So self-similarity implies that the object is similar to a part of itself, which in turn is similar to an even smaller part, and so on. So in the case of the Koch curve, the self-similarity has three important properties. It's infinite. So the self-similarity takes place over infinitely many levels of magnification. So, here we zoomed in twice, I guess, right? You can zoom in 1,000,000,000 times and you'll still see the same thing. The number of times you decide to zoom does not matter. That's what property 1 is saying. It's universal. So the same self-similarity occurs along every part of the curve. It doesn't matter where you decide to zoom in. It's exact. We see the exact same image at every level of magnification. So if you think about it, that's kind of strange, isn't it? That you have this object that's kind of inside of itself all of the time. Most objects you encounter in the real world are not like this, of course, right? So if you took me and started like zooming in on like my hand, right? You're not going to see a bunch of little hands, right? As you zoom in on my hand, you're going to start seeing different things. But this figure here, you can zoom in as much as you want, and you will be seeing the exact same object. So this object is like inside of itself infinitely many times. Whatever language you want to put with that, it's very strange. So there are many objects in nature that exhibit some form of self-similarity, even if in nature self-similarity can never be infinite. Like whatever object you're focusing on in nature, if you zoom in enough, you're just looking at atoms or whatever. So you're not going to see the same thing at every level of magnification. But there are certain things in nature like cauliflower florets where you look at them and here's a big picture of it zoomed out, and then when you zoom in, you see basically the same thing. So as you zoom in or zoom out, you're basically seeing the same little pattern, right? This little floret pattern. So one can informally say that the Koch snowflake is a two-dimensional mathematical blueprint for the structure of things like cauliflowers. Here are some interesting facts about the snowflake. One of the most surprising things about the snowflake is that it has a relatively small area, but the perimeter of it is infinite. Okay, so think about that for a second. You have a geometric shape that basically looks like, where is it? Here, okay. This is a geometric shape with pretty small area. I mean, I don't know, it has maybe area less than 10 or something. You could think about putting a rectangle around it with area 10. So it's a pretty small area. But the boundary of it, so if you were to like walk along this perimeter of it, the perimeter is infinitely long. If you think back to your geometry days, the last time you took geometry, you will not encounter figures like this. So you think about like squares, triangles, rectangles, diamonds, whatever. All of these figures have finite shape and their perimeter is finite. But not so with this figure. It's finite area, but its perimeter is infinite. Okay, that's kind of strange. Where were we? Okay. Yeah, so it seems to defy common sense. If you have a shape with finite area, how could it possibly take you an infinite amount of time to walk around its perimeter? That makes no sense. So let's think about why that would be. At each step, we replace a side by 4 sides that are a third as long. Thus, at any given step, the perimeter P is 4/3 times the perimeter at the previous step. So here at step 1, notice the perimeter has length 3, right? Just 1, 1, 1. Now at the next step, what is the perimeter? Well, it's a third plus a third plus a third plus a third is 4/3. So this side length that used to be 1 has now turned into a crinkled edge with side length 4/3. Same for this, same for this. So here we have 4/3 plus 4/3 plus 4/3 is the new length. And same thing here, right? So when you take this edge here, this a third edge, is now going to grow. Now it becomes a ninth plus a ninth plus a ninth plus a ninth, which is 4/9. So you took something that was length a third and replaced it with something of length 4/9. So the perimeter keeps growing every time you do this, and in fact you can show that this growth is fast enough to produce an infinite perimeter. So basically every single time you replace an edge, a single edge, you're introducing a factor of, some power of a third. And the growth of all these powers of a third that you're growing here makes the total perimeter infinite. So the area of the snowflake is less than the area of the circle that circumscribes the seed triangle. So just draw a circle around the original triangle. Every subsequent step will stay inside that circle. So the area of the Koch snowflake is exactly 8/5 times the area of the seed triangle. So don't worry about this 8/5, but just notice that, look, I know what the area of a circle is. So whatever the area of the circle is, that's bigger than the area of the snowflake. So, and this circle is not very big. Okay, so this Koch snowflake, just to sum up here, has an infinite boundary because every time you do this replacement thing, you're growing the boundary by quite a bit, but the area is finite. So just start by writing a circle around the original triangle. Every subsequent step stays inside that circle. So you're not going to grow the circle or the snowflake beyond the circle. Therefore, the area of the snowflake is less than the area of that circle. So having a very large boundary packed within a small area is an important characteristic of many self-similar shapes in nature. So long boundaries improve functionality, whereas small volumes keep energy costs down. Okay, so that's a nice little fact. So just for example here, the vascular system of veins and arteries in the human body is a perfect example of the trade-off that nature makes between length and volume. So whereas veins, arteries, and capillaries take up only a small fraction of the body's volume, their reach, or their perimeter, whatever word you want to use there, is enormous. So laid end to end, the veins, arteries, and capillaries of a single human being would extend more than 40,000 miles. Okay? So in other words, what this thing is saying to you is there's a shape of things inside your body whose perimeter, in quotes, is 40,000 miles. But of course, the overall area or volume that the system takes up in your body is pretty small. So here are some properties of the snowflake. It's exact, and it has exact and universal self-similarity. You can zoom in or zoom out as much as you want, and you will see the same thing. Its perimeter is infinite, but its area is finite. And it's like really finite, if that even makes sense. So the area of the seed triangle was, whatever it was, the area of an equilateral triangle was side length 1, and then you just multiply that times 1.6. So it's kind of a funny figure. You can zoom in, zoom out as much as you want. It contains finite area, but the boundary itself is infinite. Okay, so let's now move on to the second fractal. The second fractal is called the Sierpinski gasket, named after the Polish mathematician Sierpinski. Just like with the Koch snowflake, the construction of the gasket starts with a solid triangle. But this time, instead of repeatedly adding smaller and smaller versions of the original triangle, we will remove them according to the following procedure. So again, last time with the Koch snowflake, we glued more and more triangles on. We added smaller and smaller triangles. This time we're going to delete smaller and smaller triangles. So to begin with, let's start with the shaded triangle ABC. This is the seed triangle. So now, instead of gluing smaller versions of the triangle onto the three sides, we're going to remove a copy of that triangle. So step 1, remove the triangle connecting the midpoints of the sides of the seed triangle. So here's the midpoint of AC, here's the midpoint of CB, here's the midpoint of AB. So we connect those dots and then we just delete what's inside of that. Okay, but once you do this, you can do it again. So now we have a new blue triangle right here, and we can pick the midpoints of the sides and connect them, and we'll get a triangle that kind of follows this mouse, and then we can delete that. And same thing up here, and same thing right here. So our next step would just be to go to all the blue shaded triangles that still exist and delete basically the middle of them. But then you can keep doing it again, right? You can keep doing this infinitely often. So here's the next step, right? And now we have 9 triangles left. So we started with 1 triangle. That 1 triangle became 3 when we deleted. The 3 triangles become 9 triangles. and so on. So at the next step, we'll have 27 triangles. So here, we'll take this blue triangle and chop it into 3 by connecting the midpoints and deleting. Same with this guy, same with this guy, etc. And we'll end up with a picture like this. So to each of the 9 shaded triangles, we apply the procedure SG, which SG just stands for go to all the blue shaded triangles and delete the middle of them, like we've been doing. The result is this gasket, which consists of 27 triangles, each at 1/8 the scale of the original triangle. So there are 9 small holes of the same size, 3 medium-sized holes, and 1 large hole in the middle. So the size of the holes that you create decreases. So on the very next step, right, we're going to get even smaller little holes. So to obtain the Sierpinski gasket, you just keep doing this over and over and over again. After a few more steps, just like with the snowflake, the figure becomes visually stable and the naked eye won't be able to tell the difference between step 1,000,000,000 and step 1,000,000,001. So at this point, we have a good rendering of the gasket itself. So this is step 7 of the process. This is what it looks like. So again, here's the big original triangle. From step 1, the big original triangle we deleted. Here are the 3 smaller triangles we deleted on the next step. And then you can see the 9 next smallest triangles that we deleted on the next step, etc. So here we get a different replacement rule. Before, we took a side and replaced it with a crinkled side. Now, every time we see a blue shaded triangle, we replace it with a blue shaded triangle with a hole shot through the middle, and the hole is determined by the midpoints of the sides. So we might think that the Sierpinski gasket is made up of a huge number of tiny triangles, and indeed that's what this picture sort of suggests here. So you see these little blue specks. You might think that all of those blue specks are tiny, tiny triangles. This is actually just an optical illusion, however. There is no solidity in the gasket. Okay, just specks of the original triangle surrounded by a sea of white triangular holes. If we were to magnify any one of those small specks, we would see more of the same, specks surrounded by white triangles. So this figure here, even though it looks like there might still be small, tiny little blue triangles, it's just an illusion. There aren't any solid blue triangles anywhere. They're just tiny little specks. Okay. So as with the Koch curve, the self-similarity of the gasket is infinite, so you can zoom in or zoom out as much as you want. You will see the same thing, universal and exact. That's what all that means. Zoom in, zoom out as much as you want, you're going to see this exact same figure. So like if you pick this tiny little spot here and zoom in, you will see this. Okay, so zoom in or zoom out as much as you want. You will see the exact same picture that you started with. So just like with the Koch snowflake, let's now think about the perimeter and area of this thing. As a geometric object that exists in two-dimensional space, the Sierpinski gasket should have an area. I mean, it's just sitting on the screen, right? The screen is a two-dimensional space. So here's this object that looks like it has some solidity, It looks like it should have some area. Okay. Well, it turns out, and again, to actually explain why this is true is beyond the scope of this course, but it turns out that the Sierpinski gasket has no area. It has 0 area. So, as it says here, right, Sierpinski gasket has 0 area. So basically what you do is you say, well, suppose it had an area. You then show that its area is smaller than any positive number. But what does it mean to be smaller than any positive number? It means you must be 0. At the same time, the boundary of the gaskets obtained at each step of the construction grows without bound. So just like with the Koch snowflake, every time you take a step in the recursive process, you introduce more boundary. The same thing is true here. So let's go back to the beginning of the construction. This guy, the boundary of this figure is whatever the length of this triangle perimeter is. But at the next step, you now have the original length, plus you have the boundary of this interior triangle. That all counts. And at the next step, you have this original outer length, plus this interior length, plus this, plus this, etc. That all counts as the boundary. Same thing with this. Every single edge, that boundary, that, what's the verb of boundary? I'm not sure. But anyway, every single edge here that borders something white counts as the boundary. Okay, so back to this slide here. Yeah, at the same time, the boundary of the gaskets obtained at each step grows without bound. So the Sierpinski gasket has an infinitely long boundary. So here are the properties of this shape. It's self-similar exactly and universally. So you can zoom in or zoom out as much as you want, and you will see the same thing. It has no area. So it's a two-dimensional figure with no area, but its perimeter is infinite. So again, if you think back to the last time you took a geometry course and think about the figures you studied there, things like triangles, rectangles, whatever, this is nothing like those figures, right? All of those figures have an area, right? I mean, a rectangle is length times width. That's its area. A triangle is 1/2 base times width, or base times height. That's its area. So you have probably never encountered something like this before. Something whose perimeter is infinitely long, but encompasses nothing, like has no area inside of it. It's very strange. So there's a surprising application of the Sierpinski gasket to one of the most vexing problems of modern life, the inconsistent reception of cell phones. A very efficient cell phone antenna must have a very large boundary. More boundary means stronger reception, but a very small area. Less area means more energy efficiency. And it needs to be self-similar. So self-similarity implies that the antenna works equally well at every frequency of the radio spectrum. Okay, so just to sum up, a good cell phone antenna needs to have a large boundary for better reception, but small area due to energy efficiency, and it needs to have self-similarity because you have to be able to zoom in or zoom out on the radio spectrum arbitrarily. So you can design a cell phone antenna based on a Sierpinski gasket, and fractal antennas based on this concept are now used not only in cell phones but also in wireless modems and GPS receivers. So the Sierpinski gasket seems like it seems like an interesting thought experiment, but you might think it has no application. But it does. You can design antennas for cell phones and GPS receivers based on the idea of the gasket. So to conclude this video, I want to show you a cute little game that sort of connects randomness to fractals in a way that's totally unexpected. So now we will introduce a recursive construction rule that involves chance, and in fact it will involve dice throwing. This construction is known as the chaos game and is attributed to Michael Barnsley, who works at Australian National University. And here's how the game goes. We start with an arbitrary triangle with vertices A, B, and C, and an honest six-sided die. Before we start, we assign 2 of the 6 possible outcomes of rolling the die to each of the vertices of the triangle. So we decide that, hey, if we roll a 1 or a 2, then we're going to choose the vertex A. If we roll a 3 or a 4, we will choose B. If we roll a 5 or a 6, then we choose C. Now these choices of numbers are arbitrary. I could have said, oh, I want 1 and 4 to correspond to A, 2 and 6 to correspond to B, 3 and 5 to correspond to C. Okay, it doesn't matter. All that you want is 2 numbers for a vertex. And now we're going to play the game. So here's how it goes. You roll the die and mark the chosen vertex. So say we roll a 5, that means that we're at vertex C. Right? Because we said that 5 or 6 means vertex C. This picture shows you rolling a 1. So let's ignore that. So let's say we roll a 5. That means we're at vertex C. Roll the die again. Say we roll a 2, so the new chosen vertex is A. We now move to the point halfway between C and A, and we mark the new position. Okay, so the original dice throw just gives us a vertex to start at. The next dice throw gives us a vertex to move to, and we choose the midpoint between them. So if we had rolled a 3 here, we would go halfway between C and B and mark that midpoint. Now we roll the die again, and we move to the point halfway between the last position and 1 and the new chosen vertex. So say we roll a 3, then we move halfway between this point here that we just chose on the previous step and B, because 3 corresponds to B. Okay, so this seems kind of complicated, but basically all we're doing is it's another recursive process where we record a previous position, and then we're going to record a new position based on the dice roll. So if we're sitting here at M1, suppose we rolled the dice and got a 5. That corresponds to C, so we'd go halfway between M1 and C, which would be right there. If we rolled a 1, we would go halfway between M1 and A, which is like right there. But since we think we rolled a B, we move halfway between M1 and B, which is about right there. We mark that position, and now we're sitting there. So now on our next dice roll, we'll either go halfway between this and C and mark that, halfway between this and B and mark that, or halfway between this and A and we'll mark that. So you just continue doing this, and you mark your current position and then go halfway between that and either A, B, or C, depending on what you roll. If you roll the die thousands of times, millions of times, you get something that looks like this. So in the beginning of this process, this is just after 50 rolls, it just looks like a triangle with some dots inside of it, right? Or like little specks of dust on the screen or something. But if you start rolling 500, 5,000, maybe even 5 million dice rolls, you will end up with a picture that looks like this. Well, why would you end up with a picture that looks like this? Who knows, right? But this is what this Australian mathematician noticed, that if you play this little die rolling game, after many, many, many rolls, you will end up with a picture that looks like the Sierpinski gasket. Okay, so let's just sum up what's happened here. We created this silly little game where we start with a triangle and we roll a die. And based on the die roll, we move halfway between where we're currently sitting, which we started at C, and where the die tells us to go, which in this case was A. So we move halfway between, now we're sitting here. Then we roll the die again. From this point, we either go halfway to C, halfway to A, halfway to B. In this case, we moved halfway to B. Now we're at this point. Now we can roll the die again. We're either going to go halfway to A, halfway to C, halfway to B. Let's say we go halfway to C, so we're right here. Then we'd roll the die again. We'd either go halfway to A, halfway to C, or halfway to B. And so on. So we just do that thousands upon thousands of times. We will get something that looks, to the naked eye, identical to the Sierpinski gasket. It's bizarre, okay? There's no reason in the world to think that this would happen, and yet it does. So the longer we play the game, the closer we get to the Sierpinski gasket. So after, say, 100,000 rolls, we couldn't tell the difference between the gasket and what we currently have from the game. So after a few more steps, the figure becomes stable. We can't tell the difference between this game-generated picture and the Sierpinski gasket, and we get the gasket itself essentially on the screen. I can't really communicate to you how surprising this is. We took a stupid little dice game, and we ended up with this picture. Why would you get this picture out of this dice game? It seems to make no sense. The chaos game is ruled by the laws of chance, right? The replacement rules that we did earlier are not ruled by the laws of chance. The replacement rules said, look, you find a blue triangle, you delete the middle of it. There's no chance involved, right? So the picture here that we generated from the dice rolling is a product of random chance. So you would think that by doing this little dice game, you would get a picture of random dots. Why wouldn't you? You're just rolling a die over and over again, right? But you don't get a collection of random dots. You get this, right? It's remarkable. And the longer you play the game, the more dots you get, the better the approximation becomes. So an important application of this is that it's possible to generate geometric fractals using simple rules based on stupid things like dice rolling. You know, it's weird. So something like this, it's not terribly applicable to the real world. It's just, you know, mathematics sometimes, it's just interesting to see connections between two things. It's interesting to see a connection between the Sierpinski gasket, which was generated by a non-random process, right, just deleting triangles, and a totally random process such as rolling dice. So if you want to see more about this, you can always Google chaos game and see what you get. Anyway, it's a pretty neat little thing. So that's it for sections 12.1 and 12.2. The big ideas from this are the replacement rules. So taking something and replacing either an edge with a crinkled edge, or maybe taking a triangle and replacing it with a triangle with a hole in the middle, in these two cases. And that's a way you can generate these wacky figures that are self-similar and have infinite boundaries, but either finite or no area. Okay, so we only have 2 sections left to go. In 12.3 and 12.4, we will turn our attention to other fractals, such as the Mandelbrot set.